Welcome back to the Deep Dive. Today we are taking, I think, the ultimate shortcut to being well-informed about one of the most complex, high-stakes engineering projects you can probably imagine.
Mhm.
We're not just looking at a vehicle. We're looking at a mobile power plant, a heavy industrial machine, and honestly, the subject of a really critical risk assessment. We're talking about the 400-volt P2 hybrid cement mixer truck.
It sounds kind of straightforward, doesn't it? Like you're just swapping out some hydraulics for a high voltage electric drive.
Right.
But we're going deep into professional consultancy report today. And this thing is designed to help an engineering team build their entire upper structure system performance and safety review process from the ground up.
So our mission today is to unpack that full roadmap. We need to decode the global compliance matrix that ensures this. This beast meets all the requirements for power, economy, comfort, but, above all else, safety.
And specifically functional safety. We're talking ISO 262 principles rooted really deeply in the design.
Yeah. So if you are an engineer, a product planner, or frankly just curious about how global safety law intersects with physics, this deep dive is your guide to avoiding mandatory recalls and, well, catastrophic liability.
What's really fascinating right out of the gate is that the sources introduce this central strategic challenge. They call it the core paradox.
Okay.
And it's that this truck has a dual legal identity. And if you misunderstand that, it's the #1 source of non-compliance risk globally.
Okay, let's unpack that then, this core paradox. When it's driving down the highway full of cement, it's legally what? An N3 heavy vehicle.
Exactly. And that classification pulls it under all the strict automotive laws, road safety regulations. That's the part everyone understands.
That's the easy part.
That's the easy part. But here is the trap. The moment that truck parks on a construction site, engages its power takeoff, the ePTO in this case, and the drum starts turning to mix or unload concrete, it fundamentally switches its legal classification. In the eyes of the regulators, it is now mobile industrial machinery.
Wow. So that dual identity immediately triggers two completely separate, and I'm guessing often contradictory regulatory systems.
That's it. You have automotive law on one side, things we all know, like ECE R100 for high voltage, or FMVSS 305 in the US, which governs road safety and crash dynamics.
And on the other side,
You have machinery law, which is a completely different world. In the EU, that's the Machinery Directive 2006/42/EC. In the US, it's OSHA 1910 regulations.
and the requirements for, say, preventing a person from being crushed inside a giant rotating drum are totally separate from protecting a high voltage battery in a car crash.
Completely separate. And this headache just gets worse when you look at the three big markets, Europe, China, and the US. Their actual regulatory philosophies are wildly different. It forces a very, very specific global strategy.
Okay, so let's contrast those. The EU is what the sources call the type approval fortress.
Yeah, that's a good way to put it. Their whole philosophy is strict pre-approval. You have to prove you're compliant through mandatory third-party audits and tons of documentation before you can legally sell a single vehicle.
No paperwork, no sale.
Simple as that.
And then you've got China. The report calls their approach the Administrative Admission Gateway.
Right. They use something called the Gung-Go system, or announcement management. You test extensively, you get your administrative admission, and that allows you to start selling. But, and this is a big but, that admission is not a final guarantee.
So what makes it so challenging?
The post-check surveillance. It's high risk and it's high frequency. China runs these routine randomized inspections on vehicles that are already on the road. So admission is really just the beginning.
You have to stay compliant.
You have to stay compliant, and they can revoke that admission fast if they find a common issue. It's less of a fortress and, more of a monitored gateway.
Which brings us to the U.S. They call it the self-certification legal minefield.
And it is the philosophical opposite of Europe. The government NHTSA specifically doesn't approve anything up front.
Good.
Nothing. The OEM just signs a piece of paper, the certificate of conformity, that basically says, we swear we comply with all the federal motor vehicle safety standards, the FMVSS.
And by signing that,
You accept unlimited legal responsibility. The report puts it really powerfully. In the U.S., your engineering documents, like your failure mode and effects analysis, your FMEA, they aren't written for the government. They're written for the courtroom. You're building the evidence for your future legal defense.
okay, so that dual legal identity vehicle versus machine is the big tripwire. Engineering teams fall into this trap because they assume whole vehicle type approval covers, well, the whole vehicle.
They do, and the sources are really clear. They often get the chassis right, but they fundamentally fail on the top half of the truck.
So let's dive into that identity crisis. It breaks down into those two modes, road mode and work mode.
Right. And it's really a case of different departments speaking totally different languages. In road mode, you've got the chassis, brakes, steering, lights, all the weight limits, and the fundamental high voltage system integrity. All of that is governed by automotive laws.
So in Europe, that's EU Regulation 2018-858, which is the foundation for whole vehicle type approval, WVTA. Now, WVTA sounds so all-encompassing. That's why the assumption is so common. What does it actually cover?
It confirms compliance with dozens of specific ECE regulations. ECE R13 for braking, R48 for lighting, R100 for high voltage safety, the list goes on. It basically just confirms the vehicle is safe to drive on public roads.
But then we get to the hidden trap, which is the work mode.
Exactly. That entire upper mixing structure, the huge rotating drum, the drive motor, the controls for the discharge chute,
Yeah.
all of that has to comply with machinery law. For Europe, that means the EU Machinery Directive, and specifically a standard called EN 12609.
And that's for concrete mixers specifically.
Yes, it covers the specific safety requirements for them. And this is where we find the fatal misconception that the sources flag as the #1 design failure.
Which is?
The belief that achieving WVTA also covers the drum and the mixing function. It's 100% false, especially in the EU's highly structured system.
So why isn't WVTA enough? Why can't you just get that and sell the truck?
Because the upper structure is legally considered a separate, bolted-on piece of machinery that just happens to be mobile.
Interesting.
This means the mixing system has to independently complete its own mechanical risk assessment. This uses principles from a standard called ISO 12100, which defines how you identify and mitigate mechanical hazards, things like entanglement, crushing, shearing.
And that risk assessment has to result in some kind of documentation, I assume.
It does. It has to lead to an EC declaration of conformity. This is basically the mechanical CE mark for the upper half of the truck.
And without that declaration,
The vehicle is incomplete. Even if the chassis has perfect WVTA, the regulator can reject the entire vehicle because the required documentation for the machinery component, the drum and its drive system, is missing or it's flawed.
that is a staggering risk. You could invest billions in a platform, and the whole vehicle gets rejected in Europe because a separate safety file for the mixer wasn't done.
Precisely. The WVTA can be revoked or just flat out refused if the regulatory office finds that the required mechanical safety declaration is missing. It's a total non-negotiable step.
So this brings us back to strategy. An OEM can't afford to design 3 totally separate vehicles for the EU, the US, and China. So what does this global one design strategy actually look like in practice?
It's all about establishing a global superset specification. The report is adamant about this. If you try to take the U.S. self-certification logic, which is reactive, it's result-oriented, and apply it to the EU's pre-approval fortress, or vice versa,
It's just not going to work.
it's a 100% compliance failure. The legal philosophies are just in direct conflict.
So the rule has to be to take the most demanding technical requirements from all the markets and build to that highest common denominator.
That's it. If standard A requires X and standard B requires 5X, you design for 5X, and that leads to a very clear strategic conclusion. The EU is the technical bottom line,
Why the EU?
because its requirements are the most rigorous in terms of documentation and mandatory pre-approval. It forces you to think about the vehicle and the machine at the same time.
But wait, a minute ago you said the U.S. sets the legal risk ceiling. Why is the EU the technical bottom line if the U.S. has a higher standard in some specific areas?
That's a great and a really necessary distinction to make. The EU dictates the completeness and the rigor of your upfront process and your paperwork. It forces the engineering team to consider both identities of the truck.
Okay.
The U.S., on the other hand, sets the ceiling on specific post-crash performance metrics and, your liability exposure. The U.S. says, we don't care how you designed it, only that after this very specific crash test, these criteria are met.
So you use the EU's process rigor to get your house in order.
Yes, to organize all the documentation. But you use the U.S. performance criteria like post-crash high voltage requirements as your highest engineering target.
That perfectly sets up our next deep dive then into high voltage safety. This is where the rubber meets the road. Literally, we've got a 400-volt system constantly exposed to conductive cement dust, sand, heavy vibration, high moisture.
It is inherently a high-risk application. And we really have to focus on the two big standards, FMVSS 305 and ECE R100. and the completely different legal outcomes they drive.
So what's the core philosophical difference here?
It is absolutely vital for the engineering team to get this. ECE R100 is focused on design compliance. It's about making sure the components, the structure, the running state,
Yeah.
that they're all safe during normal operation. It's your ticket to operate.
But FMVSS 305 in the U.S.?
It only cares about the aftermath. It's all about post-crash result safety. It focuses entirely on protecting rescue personnel and occupants after a severe 30-mile-per-hour collision. The sources put it very starkly. ECER 100 is a ticket. FMVSS 305 is a trial.
Let's start with technical pillar 1 then, isolation resistance. This is the resistance between the high voltage wiring and the metal chassis ground, right?
Correct. And this is where the most dangerous gap exists between the two major global standards.
Okay, let's talk numbers. What are the specific requirements for DC systems like this?
For DC systems, ECE R100, which is the cornerstone of EU AGV compliance, mandates a minimum isolation resistance of at least 100 ohms per volt.
So for our 400-volt system, that's what, 40,000 ohms? 40?
Exactly.
Okay.
100 ohms times 400 volts is just 40 key.
Now, 40 key sounds like a decent amount of resistance to a layperson, but in a long-term, high-moisture conductive environment like a cement mixer, that feels dangerously low.
It is functionally low for a 5+ year vehicle life in that environment. And this is why FMVSS 305 is so much more demanding. It mandates a ratio of at least 500 ohms per volt.
Okay, so for the same 400V system, that minimum jumps to 200 key.
200 kiloohms, yes.
So we have a major difference, as the report calls it, where the U.S. standard is 5 times more stringent than the EU minimum.
It is. And if an OEM focuses only on hitting that ECE R100 minimum, they are building a guaranteed failure point for the U.S. market.
And it's not just about compliance, is it?
Not at all. You're not just non-compliant with FMVSS 305. Operating at 40 key in an environment where conductive cement dust is constantly settling on harnesses and connectors means that insulation resistance is going to grade, and fast.
So over 5 years.
Over 5 years, that 40 key could easily drop below safe thresholds, which massively increases the risk of electrocution, and that is a criminal liability issue globally.
So the engineering takeaway is crystal clear. The internal design standard must be 500 ohms per volt or higher. That gives you the defensible safety margin for the harsh environment and meets the U.S. legal ceiling at the same time.
Yes. And it goes beyond just static isolation. FMVSS 305 is intensely focused on high voltage retention post-crash. ECE R100 is less prescriptive on the timing here, but the U.S. standard is absolutely unforgiving.
What is that precise requirement?
FMVSS 305 strictly requires that high voltage power must be removed. So the remaining voltage has to drop below the hazardous threshold of 60 volts DC within 5 seconds or less after the moment of impact.
5 seconds. That is an incredibly short amount of time.
It is. And this short timeline is a common failure point because the high voltage capacitors inside the motor inverter, the DC-DC converter, and other power electronics, they naturally store a significant amount of charge.
So passive discharge circuits just aren't fast enough.
They often aren't. And if those circuits are damaged in the crash or just too slow, the system will still be energized above 60 volts DC after that 5-second window. And that's non-compliance and a massive legal risk if a first responder touches the chassis.
So you need active discharge circuits, and those circuits have to be proven to survive the very crash they're designed to protect against.
Precisely. You have to verify not just the discharge time, but the structural integrity and the resilience of the active components that are responsible for that fast voltage removal. This is a critical testing scenario that FMVSS 305 mandates, unlike ECE R100's focus on the running state.
Okay, let's pivot to technical pillar 2, equipotential bonding. If isolation resistance protects the wiring's integrity, bonding protects the person who touches the vehicle.
Correct. This addresses the huge physical and potential criminal risk of the entire vehicle body becoming live. The risk scenario is very straightforward. A crash or physical failure causes a 400V short to the chassis.
And if that enormous metal mixing drum isn't properly grounded?
It becomes a deadly conductor.
And the sources highlight a typical failure mode here, which is relying on the incidental grounding through greased roller bearings.
That's cited as a classic, incredibly dangerous non-compliance case. Greased bearings are designed to minimize friction, not to maximize electrical conductivity. They naturally have a high, unreliable resistance.
So what's the mandatory requirement?
The requirement for safety is dedicated, permanent bonding between all the conductive parts: the chassis, the subframe, the drum, and the cabin.
And there's a very specific, measurable requirement for this, right?
Yes. The requirement, which is supported by standards like ECE R100 and the Chinese GB R10384, is that the measured resistance between any two conductive points on the vehicle structure must be strictly less than zero point 0.1 ohms.
Zero point 0.1 ohms. Why such an extremely low threshold?
Because a low resistance path ensures that if a fault occurs, the high fault current is immediately shunted to ground, and that triggers the protection system, like a fuse blowing or a contactor opening, before the voltage can build up to lethal levels across the vehicle body.
And how do you prove that measurement? I remember the sources mentioned the four-wire method.
Yes, the four-wire Kelvin method is mandatory for this kind of verification. You can't just use a simple two-wire multimeter because that includes the resistance of your test leads and contacts.
Okay.
The Kelvin method uses separate sets of leads for current injection and voltage measurement, which eliminates those parasitic resistances and gives you a highly accurate reading of the actual structural resistance.
And critically, this has to be verified post-crash.
For a solid legal defense, absolutely. That less than 0.1 ohm compliance must be verified after the crash test.
So the engineering solution can't be incidental contact. It has to be dedicated, low-resistance connections.
Exactly. We're talking about things like robust carbon brush slip rings or massive braided copper straps that permanently link the rotating drum assembly back to the main chassis ground point. You have to ensure that pathway is reliable, regardless of lubrication or movement.
And finally in this section, let's touch on environmental and thermal robustness. This is pretty unique to this heavy-duty application. Why is a seemingly robust standard like IP67 completely insufficient for this truck?
Well, IP67 is great for dust and temporary immersion, like driving through a flooded street. But the operational reality of a cement mixer is far, far harsher. These vehicles are cleaned daily, sometimes multiple times a day, with industrial high-pressure washers.
Right, often with high-temperature steam or water jets to dissolve caked on cement.
And that pressure and heat will just destroy a standard IP67 seal over time. It turns it into a sieve.
So the ingress protection has to be much higher.
Much higher. The sources are emphatic that components in those areas, especially connectors, motor casings, wiring junction boxes, they have to achieve the rigorous IP6K9K rating.
And that's the one for high-pressure, high-temperature jets.
It is. Anything less will result in moisture ingress, insulation degradation, and eventual electrical failure. It's a guaranteed non-compliance.
And before we leave HV, we have to talk about thermal safety, specifically the requirement from China's GB 38031. This is a life-and-death standard.
It is arguably one of the most stringent battery safety rules in the world. GB 38031 mandates that the battery system, the high-voltage pack, has to be designed to prevent fire or explosion for at least 5 minutes after a thermal runaway event is detected in a single cell.
5 minutes. That sounds very precise.
Mm-hmm.
What is the explicit purpose of that 5-minute window?
It's the mandatory non-negotiable escape time. It gives the driver and any workers nearby the necessary window to safely exit the vehicle and the immediate area before that thermal event propagates into a catastrophic system failure, like a fire or an explosion.
And meeting that requires some pretty advanced engineering, I'd imagine.
Oh, absolutely. We're talking advanced cell-to-cell barrier design, heat insulation management, and robust directed venting systems to channel those hot gases away from the cabin and other critical areas.
We've established the severe electrical risks. Now we need to pivot, following that machinery directive, to mechanical and functional safety. This is where the quiet nature of the electric drive system introduces a new and potentially catastrophic layer of hazard.
The primary risk scenario here, the one that immediately drives you to the highest safety classification, is the accidental startup or rotation of the mixer drum, specifically when workers are inside doing cleaning or maintenance.
And the sources noted this isn't some theoretical risk. Workers routinely enter the drum for cleaning. It's a known, frequent operational thing.
It is a critical and, more importantly, a foreseeable risk. So let's apply the functional safety analysis, the HRR, the hazard analysis, and risk assessment to that scenario. Unexpected drum rotation while a person is inside.
Okay, using the ISO 26262 framework, let's start with severity, or S.
Severity is S3. A person inside a massive rotating steel drum. They can't escape the crushing and shearing forces. This leads almost instantaneously to fatal or permanent life-changing injury, no question.
Okay, S3. What about controllability, C?
Controllability is C3. Once you're inside that drum, the worker has virtually zero control over the situation if it starts to move unexpectedly.
And exposure, E.
Exposure is high, E3, because cleaning is a routine, mandatory activity. It's necessary for operational maintenance.
So severity 3, controllability 3, high exposure. That combination forces the highest possible functional safety conclusion, doesn't it?
It does. The safety function that controls the drum's rotation must achieve an uncompromising ASIL D. That's Automotive Safety Integrity Level D.
Or for those more familiar with the industrial standards from the machinery directive.
The equivalent level is Performance Level E Category 4, PLE Category 4.
Let's pause on that. For our listeners who are less familiar with the industrial side, what does PLE Category 4 mean in simple terms? Why is it equivalent to ASIL D?
They're both the highest safety ratings you can get. PLE Category 4 means the safety circuit, the physical pathway that stops the drum from turning, has to be robust enough to withstand two simultaneous independent faults and still perform its safety function.
So it's about redundancy.
It's full redundancy, continuous fault detection, and a virtually zero probability of failure. It's the gold standard for protecting against fatal mechanical accidents.
And failing to classify this known severe risk, a person being crushed inside the drum at that absolute highest level, is not just a technical error. The report flags it as a major legal risk.
Oh, it's a huge legal risk. It would be interpreted as the OEM knowingly downplaying a fatal hazard. If an accident happens and the ASIL rating was set lower, say ASIL C, a court would say the OEM accepted a higher risk tolerance for a known fatality.
That they failed their fundamental duty of care.
Exactly.
So given that ASIL D is required, how do you actually implement that to physically stop the drum from turning?
The imperative here is a hardware-based safe torque off, or STO. This is the core safety mechanism. STO has to be a mandatory hardwired hardware-level function that physically removes the drive energy from the motor.
And what's the red line here? What must the system absolutely not accept?
It must not accept a software-only stop command. The system has to physically remove the power from the inverter gate drives, which prevents the motor from generating any torque.
And that red mushroom head emergency stop button, the e-stop,
Must be hardwired to directly trigger that dual-channel STO circuit.
why does it have to bypass the communication bus, like the CAN bus?
Because the CAN bus is susceptible to faults. It can get overloaded, it can have communication failure, a software glitch could create latency. If you rely on the CAN bus to transmit the e-stop command, the system is fundamentally non-compliant with ASIL D.
Because you've introduced a single point of failure.
A single point of failure and unacceptable latency into the most critical safety function you have. The e-stop signal has to physically and immediately interrupt the power path, completely independent of any software state.
That is a crucial design distinction. Now, let's talk about the silent operation risk. Since this is an electric stirring system, it can be nearly silent compared to a traditional diesel hydraulic setup.
Right. And this creates a violation of core machinery safety principles because workers can easily misjudge whether the equipment is live, active, or safe. The old assumption that if it's running, it's loud is just gone.
So how do we mitigate that silent threat?
The mitigation is a mandatory 3 to 5 second audible and visual pre-warning. This is required by standards like EN 12609.
And what does that look like?
When an operator starts the mixing or unloading function, a buzzer generating at least 65 decibels and a flashing light have to activate for several seconds before the motor is allowed to output any torque. It provides a perceptible warning that the equipment is about to move.
And finally, what about the physical interlocks that you need to meet the machinery directive and enforce that ASIL D state?
The design has to incorporate two primary layers of physical protection. First, mechanical locking devices for the drum pins or blocks that are manually engaged during cleaning or maintenance. And second, safety interlock switches on all the cleaning and inspection access points, like the manholes you use to enter the drum or access ladders. And crucially, these interlock switches must link directly via hardwiring to the STO function.
So opening that manhole has to immediately enforce the safe state.
It must immediately enforce the ASIL D safe state, no software in between.
This is where the consultancy report moves, I think, entirely into legal strategy.
Yeah.
We need to talk about the FMVSS 305HV crash FMEA and the complete mindset shift that's required for drafting this document. You're no longer writing for an internal review board.
That's the most difficult transition for engineers to make. The mindset shift is realizing the FMEA, the failure mode and effects analysis, is no longer just an internal risk management tool. In the U.S. system, it is courtroom evidence.
So who are the real readers?
The true readers are NHTSA investigators, accident reconstruction experts, and most importantly, plaintiff lawyers. The whole document has to be written to achieve what the report calls defensible compliance.
And this changes how you score the severity of a failure mode. We talked earlier about severity honesty.
It's absolutely essential. For any failure mode that results in high voltage exposure post-crash, a short circuit, a broken wire, the FMEA severity score, the S score, must be a 9 or a 10.
The maximum.
If the potential outcome is fatal or a permanent injury, you have to use the maximum severity score allowed in your methodology.
Why is this so strict? What if an engineering team tries to score a fatal risk lower, say an S7, to make the overall risk priority number look more acceptable?
That lower score is a death sentence in court. It will be interpreted as the OEM knowingly downplaying the risk.
Wow.
The plaintiff's lawyer will stand up and argue the company assessed the potential for electrocution, which their own documents admit is fatal, yet they scored it as a moderate risk. This shows a willful failure of their duty of care. You have to be brutally honest about the consequence.
The report also mentions specific legal phrasing required around foreseeability. That sounds like insurance against common legal arguments.
It is exactly that. The FMEA has to explicitly include language stating that failure modes, like an HV harness being pulled out, contactors welding shut, a grounding strap shearing off, are reasonably foreseeable during FMVSS-defined crash events.
And if that language is missing?
Lawyers will argue the OEM failed its duty of care because they never even considered standard, predictable failure modes during a collision.
So you're not just identifying the failure. You're explicitly accepting that the failure is a known possibility in a crash.
Precisely. And this leads to the anti-software dependency clause that has to govern the FMEA's recommended actions. The protection has to be physical, irreversible, and robust enough to survive the crash dynamics.
Can you give me a concrete example of that?
Sure.
Physical protection versus an unacceptable software dependency.
Sure. Physical protection means things like mandated pyro fuses little explosive devices that cut the current path milliseconds after a sensor detects a crash, and passive discharge circuits.
And what's an example of an unacceptable dependency?
A common legal failure point is relying on the insulation monitoring device, the IMD, as the sole post-crash protection.
Why is the IMD, which is designed to monitor insulation resistance, not enough for a legal defense?
Because the IMD relies on software and communication. If the crash causes a communication failure or the control unit that houses the IMD software gets damaged, that protection just vanishes. A lawyer can argue you relied on fragile software when physical, irreversible mechanisms were available and known.
The protection has to be physical. Mechanical isolation is preferred over software sensing.
Yes.
Okay, so we have this legally robust FMEA. How do we make sure it integrates seamlessly into the ISO 26262 safety case that the engineers are required to maintain?
Well, the HV Crash FMEA isn't a standalone document. It is the critical evidence that supports the ASIL safety goals. The sources demand absolute traceability.
So it's a chain of logic.
It's a chain. The FMEA identifies the severity of the electrical hazard post-crash as a 10. That feeds into the HARA, which then sets the safety goal, or SG.
So the safety goal, for instance, prevent personnel from contacting dangerous HV post-crash, that has to be classified ASIL D because the FMEA confirmed the severity is maximal. That's the ASIL consistency you need.
Flawless consistency is mandatory. If the FMEA says S is 10, the HRA has to reflect that, which leads to ASIL D. And then the final step is verification. The actual FMVSS 305 collision test reports, the ones showing the crashed vehicle meeting the 60-volt drop and the 0.1 ohm bonding requirement, are your ultimate validation evidence that these crash-related safety goals have been met.
And this all rolls up into the execution framework, the hard gate review system. This is where strategic decisions become mandatory corporate checkpoint items.
Exactly. These gate reviews, like Gate B for design freeze or Gate D for started production, they have to be hard gates. You cannot advance the project if key legal and technical documents are missing, incomplete, or unsigned.
So which key document has to be approved by, say, Gate B?
The approved, legally reviewed HV Crash FMEA is the mandatory output of the design freeze gate. This forces legal input early in the process, which prevents incredibly costly late-stage redesigns.
And it doesn't stop at the design phase.
No, production consistency, or COP, is critical. Every single vehicle that comes off the assembly line has to undergo mandated HV safety tests.
What are they testing on every single truck?
Insulation resistance, equipotential bonding continuity, and e-stop functionality. You need documented evidence that the safety characteristics required for certification are present in every single production unit.
And this standard has to flow down the supply chain. If your Tier 1 HV supplier gives you a component that only meets the ECE R100 minimum,
that component is non-conforming, period. It doesn't matter if it's going into an EU-bound truck or a US-bound truck. The HV safety specification you issue to your suppliers has to explicitly mandate FMVSS 305 compliance as the design ceiling. The OEM must demand the highest global standard from its partners to maintain its own legal defensibility.
Okay. Beyond the existential threats of electrocution and crushing, there are several auxiliary compliance areas that are critical for getting full certification and just ensuring reliability on the construction site. Let's start with electromagnetic compatibility, EMC.
The primary source of interference is the 400V inverter. It uses pulse width modulation, PWM, to efficiently drive the motor, but that high-frequency switching creates a massive amount of electromagnetic interference, or EMI.
And if that noise is unshielded or poorly managed,
It can couple into the low-voltage control systems.
what's the worst-case consequence if the inverter is broadcasting too much noise?
An immediate, non-negotiable recall. EMI can cause critical safety systems like the ABS or the electronic braking system, the EBS, to glitch or malfunction. That could lead to a loss of vehicle control.
So what's the strategy?
The strategy mandates that the electric upper structure is certified as an electrical subassembly, or ESA. It has to undergo independent ECE R10 testing first, and then it's followed by whole vehicle verification.
And the sources recommend a massive overshoot on the standard, not just for the road, but for the job site.
Yes. For the inverter and controller, the design standard has to be the highest level. See ISPR 25 Class 5. Standard automotive levels might be Class 3 or 4. But Class 5 is required here because this truck operates on construction sites that rely heavily on sensitive equipment.
Things like
VHF and UHF radio for site coordination, for tower crane control. Achieving Class 5 ensures the truck doesn't interfere with its own critical systems or the surrounding communication and control infrastructure.
next up, acoustic safety. This is that fascinating, quiet, loud conflict that's unique to this kind of electric hybrid vehicle. You're facing two completely opposing pressures at the same time.
It's a real engineering paradox. On one hand, you have the Acoustic Vehicle Alerting System, or AVS. Electric vehicles are too quiet at low speeds, which is a risk to pedestrians. So the EU, with UN R138, mandates sound up to 20 kilometers per hour and strictly prohibits the driver from pausing or turning it off. The US, with FMVSS 141, requires sound up to 30 kilometers per hour and also mandates a specific stationary sound when the vehicle is in drive or reverse.
So you need a sound that can't be turned off, and it has to operate up to different speeds in different markets.
Correct. The solution can't be two separate hardware systems. It has to be a single, configurable software system that implements the stricter of the two requirements for each mode.
For example.
You'd use the wider speed range from the US standard, but you'd make sure the no pause button logic from the EU standard is always active.
But that quiet requirement clashes violently with the loud requirement of the job site, the backup alarm dilemma.
OSHA, the Occupational Safety and Health Administration, demands highly audible backup alarms, often exceeding 90 decibels to protect workers in extremely noisy construction environments.
Yeah. But if this truck is operating in a dense urban area at 2 in the morning, local noise ordinances often impose limits far below that, frequently less than 60 decibels at the property line.
And that traditional high-frequency beep, beep, beep alarm is a guaranteed source of neighborhood complaints and fines.
It's a classic dilemma. You need it loud right near the hazard, but quiet everywhere else.
And the report's intelligence solution is the mandatory implementation of broadband or white noise alarms.
What makes a white noise alarm the solution here?
It's a really smart engineering compromise that's based on physics. A traditional pure tone alarm, that beep beep, travels a long way and penetrates noise barriers easily. A broadband alarm sounds more like a shush or a hissing sound.
So it uses a broad range of frequencies.
Exactly. And while they achieve high sound pressure right near the truck, so workers hear it clearly, meeting the 90 dB mandate, their sound energy dissipates very rapidly over distance.
So the sound drops below that 60 dB limit much faster, which solves the environmental complaint problem while still keeping the people right around the vehicle safe.
Exactly. They are highly localized, they provide directional safety, and they adhere to environmental noise restrictions. It solves the quiet, loud conflict.
Okay, finally, let's wrap up with HMI safety. The human-machine interface. Clear display of the vehicle's state is vital, particularly with a high-voltage system.
The HMI has to be unambiguous. We need clear, mandated state displays. Things like a big ready light indicating the HV system is energized and the truck can move.
And fault indicators?
Yes. An insulation fault indicator to show that 200 key resistance minimum has been breached, and a power limited or derating indicator, which tells the operator if the system is restricting power due to thermal or electrical issues. Ambiguous displays lead directly to operator error.
And the safety logic for remote control, which is often used for positioning the mixer chute, that has to be addressed too.
It does. Any remote control function requires built-in safety mechanisms like tilt detection and a communication watchdog timer. If the operator drops the controller or the signal is lost for even milliseconds, that watchdog timer has to immediately force the system into the hardware-based save torque off state.
Preventing any runaway operation.
Exactly. It prevents runaway operation of the mixer drum or the chute in an unsupervised state.
We've covered a massive amount of ground today, from the regulatory philosophy of the type approval fortress to the specific requirement for a 500 ohms per volt engineering rule and the necessity of drafting legal documents, the FMEAA, specifically for a plaintiff's lawyer.
The core message of this consultancy report, it really remains the same. The 400V hybrid cement mixer truck is arguably one of the highest regulatory risk commercial vehicle types out there today.
And that's because of that complex intersection of high voltage, high kinetic energy, silent operation, and that dual regulatory identity vehicle and machinery.
Right. Compliance is just not negotiable, and it has to be embedded in the design process from the earliest phase, from concept freeze, all the way through that hard gate review system.
We saw that the U.S. market, despite having the least amount of pre-approval, actually imposes the highest level of legal risk. It forces engineers to prove safety in court.
And the EU, meanwhile, dictates the highest level of technical and documentation rigor, forcing that dual identity consideration right from the start.
And this leads us to our final provocative thought for you to consider, which is really the ultimate strategic conclusion from all of this.
The choice of your design baseline is the fundamental decision that dictates the project's success or its failure. If your engineering choice is driven by cost reduction that falls below the most rigorous accident-proof standard, which for HD safety is FMVSS 305, the ultimate financial and legal cost will be paid tenfold.
And that cost comes in the form of a recall, a production halt, or even criminal liability after a major failure.
The design isn't successful until it can prove, in front of a jury or a regulator, that the OEM has thought of the worst-case scenario, the crash, the crushing, the electrocution, and has mitigated it with physical, hardwired defenses.
Not just relying on software or low minimum standards.
No. The burden of proof demands that the design demonstrate the OEM's duty of care. That means the documents have to honestly and rigorously reflect the potentially fatal severity of a high-voltage failure in a real-world collision. It's about designing for the worst day, not the average day.
A truly sobering yet absolutely essential roadmap for anyone navigating this complex global engineering landscape. Thank you for joining us for the deep dive.